Hello everybody, and welcome to our last lesson for Chapter 6, 6.6 Inverse Functions. We are talking about inverse functions today, and they have something in common with the pairs of symbols or operations that I've written here. And adding and subtracting, multiplying and dividing, square root and squared. Hopefully you are thinking in your head, hey, those are opposites of each other, or they undo each other. And so today what we're talking about is entire functions, not just individual operations, but entire functions that are opposites or that undo each other. So they are opposites. And so for each ordered pair, x and y, the x's and the y's just simply switch places. All right, the graph of an inverse function is also an opposite or a reflection of the original function, and that occurs over the line y equals x, kind of a diagonal line on a graph. Our notation for an inverse function is f, -1. That's what it looks like, is a little -1 as an exponent, but you pronounce it as f inverse. The name is f inverse, all right? So let's take a look at a graph and a pair of tables here. So if you'll notice here on our tables, we have the actual equation for the function as well. And then we have a graph. So we have graph, table, and function, all three. And then our inverse is also represented in algebraic or function form. It's represented by a table and also a graph. All right, so let's take a look at the table and see what we notice. Notice that for every x value on the original function, it matches up with a y value on the inverse. And the opposite is also true. The y's match up with the x from the inverse. And that happens for all of the ordered pairs here. So just to reiterate, the x and y values switch places. Okay. There is another thing that we talk about when we talk about inverse functions, and that is the inverse also a function? So we're starting with a function for our original equation, and what we want to know is the inverse, when we take the inverse, is it also a function? And there's a very simple test to decide if it is or not. It's called the horizontal line test. And the horizontal line test says that the inverse of a function f is also a function itself if and only if. That's the abbreviation for if and only if. And then let me give you that conditional. It says that no horizontal line intersects the function or the graph more than once. So we'll say graph of f more than once. So if it passes the horizontal line test, that means that a horizontal line only crosses the function once. If it fails the horizontal line test, it crosses more than once. So if we take a look at this first one, it looks like a cubic function, and the red is our horizontal line. I'd like for you to go ahead and take your writing instrument for a second and take your pen or pencil and just pretend that that's your horizontal line and go up and down across this graph. How many times do you cross? Is there ever a place where it crosses more than once? And the answer should be no. So that means since it only crosses once, it has passed the horizontal line test, and the inverse is a function. If it does not pass the horizontal line test, as you can see here, we crossed twice, then the inverse is not a function. So now we're going to talk about inverses and finding those algebraically instead of by a graph or a set of tables. So we are ready now to move on to the inside of the foldable. So let's take a look over here, and we want to look at finding the inverse algebraically. I'm not going to read through all of these steps right now. There is one thing that I want to point out though on number 4. I just want to put a little note that we will need to look at restricting the domain or range anytime that the function isn't linear. So we'll talk about that as we get to it, but I just want to make that note there so that it's there for you as you go through additional problems later. So the first thing that we want to do is determine if the inverse is a function, and then we want to find that inverse. So I've drawn my horizontal line here. I'm going to use that for my horizontal line test here in a minute, but I guess I need to plot my function if I'm going to determine if the inverse is a function. So let's go to Desmos. And here is my function. Notice that I've plotted that dashed line at y equals x, and then I have my function f of x is equal to 3x minus 1. I have a point at 0, -1, and it looks like I also have a point at 2, 5. So I'm going to plot those and use those to plot my line. So 0, -1, and 2, 5, and I can plot my line. All right, so let's do horizontal line test. I'm going to use this purple line that I've drawn here. You're going to use your pen or pencil. And as I run this across, I see no places where I have more than one crossing point, so I'm good. My inverse is a function. So let's just go ahead and make ourselves a note of that the inverse is a function. And so now we're ready to solve for that inverse. So solving involves, again, the 5 steps. We're going to go through them one by one. So the first thing that we need to do is change f of x to be y. Sometimes y will already be there, but most of the time it's written in function notation. The second thing is switch the x and the y variables. We've got to swap those out. So everywhere I see x, I'm going to put y, and vice versa. So x is equal to 3y minus 1. And now this just becomes a algebra problem just like any other problem that you've solved since middle school. I need to, let's go ahead and make a couple notes here. This is step 1, this is step 2, and now I'm about to do step 3. That way we can keep those in order and keep track. So if I solve for y, I'm going to have plus 1 on both sides, and that gives me, these cancel, and I have x plus 1 is equal to 3y, and then divide by 3 to end up with x plus 1 over 3 is equal to y. All right, so we have solved. Number 4, restricting the domain and range. Well, we do have a linear function, so number 4 is not applicable. All right, we can take that function and go ahead and rewrite it in function notation if we want to, that inverse function. So we would say f inverse of x is equal to x plus 1 over 3. So now that we have our inverse, let's go ahead and plot that inverse. So let's look at Desmos. And I've called this function g of x just to make a distinction from f of x. And I'm going to say that it's x plus 1 over 3. And you can see that it is an exact mirror image, so we did do our math right. And I'm going to pick some points here. I'll have the point -1, 0 and 5, 2. So if we go back over here, I have -1, 0, and I have 5, 2, and I can draw my graph. And that's what my lines look like. Again, the inverse is a function. We determined that at the beginning. So this was step number 5, plotting the graph. All right, let's do the same thing on this next one. So now we're on number 2, and the first thing I want to do is determine if we have a function or not. So I'm going to plot f of x equals x squared. Notice that this one tells us already that we're restricting the domain. Remember that whenever we have a root or a power, that's a possibility. Sometimes it's in the problem statement, sometimes we have to deal with it in the answer, sometimes both. All right, so let's look at problem number 2. And here's our original function. Again, the y equals x line, and then f of x is equal to x squared. The way that you put a restriction on our domain or range is to put it into brackets like you see there. So notice that instead of a quadratic, we have half a quadratic. I can pick out points at 0, 0, 1, 1, and 2, 4, and go ahead and plot those. So 0, 0, 1, 1, and 2, 4. And I'm going to draw my half parabola. Half a parabola because we've restricted the domain. Now we need to do our horizontal line test. And you're using your pen or pencil. I'm going to come up through here, and I don't see anywhere where I cross more than once, so I pass the horizontal line test, and that means that my inverse is a function. If it had been the entire parabola, if we hadn't restricted the domain in the problem statement, then the inverse would not be a function. All right, so let's go ahead and find our inverse now. So I'm going to go through the same steps. Step 1 of changing f of x to be y. Step 2 of switching x and y. Okay, and then step 3 is to solve. And this is going to be a pretty easy one to solve. The opposite of squaring is square rooting, so I'm going to take the square root of both sides. The root and the power cancel, they're both 2, and I'm left with plus or minus square root of x is equal to y. Now, we've solved for our inverse, but we had a restriction on the domain, okay, on the x values. Remember, x is domain. So since we had a restriction to start with on our domain, we have to do the same thing on our opposite or inverse, but with the opposite. So we need to restrict our range. All right, so we need this function to always be positive. Right now, we say positive and negative. And so in order to restrict the range to be y greater than or equal to 0, I need that square root of x to always come out and be positive, not be taking the negative of my number. So I am going to get rid of the plus and minus. So step number 3 was this. Step number 4 is that I'm going to get rid of the plus and minus by restricting my range. Sorry, that 4 goes over there with my restriction. And now I can write this in function notation. So f inverse is equal to square root of x. Again, we got rid of the positive and negative. It's just a plain old square root of x, so it's always going to be positive. All right, step 5 is to plot. So let's plot f of x, or f inverse of x is equal to square root of x. I called that g of x, and you can see that it is a perfect mirror image. So I have those opposite points, and I can plot. Let's plot our points at 0, 0, 1, 1, and at 4, 2. And then I can draw my radical function. Kind of looks like a sideways half parabola. So we're ready to move on to the next problem. This time we have a square root. So keep in the back of your head, we have a root. We're probably going to end up having to think about restricting domain or range. So let's go ahead and take a look at our function and decide if it is going to have an inverse that's also a function. So back to Desmos. And I'm going to just show only my original function right now. Notice that our y values don't go past 0, all right? Anytime that you plot a square root function, we talked about this earlier in the chapter, it looks kind of like a half sideways parabola. It's not, because it hasn't been translated up or down, it never crosses the x-axis. So let's go ahead. It looks like I can plot a point at 3, 0, and I can also plot a point at 7, 4. So I'm going to plot those points. Anything else is going to be off my graph, so I'll just stick with those 2 points for now. So let's go ahead and plot a point at 3, 0, and then at 7, 4. And my graph is a curve, so it's going to look something like that. All right, horizontal line test time. Take your pencil or pen and run it up and down this. Is there any place where you cross more than once? And the answer is no. So that means it passes the horizontal line test and the inverse is a function. So the inverse is a function. All right, let's go ahead and find the actual inverse. Step 1, change to y. Step 2, switch x and y. Step 3, solve. So we're going to solve for our new y value. First thing I want to do is get rid of the 2 that's out in front because I want to isolate the root so that I can square it. So these 2's will cancel, leaving me with x over 2 is equal to the square root of y minus 3. And then in order to get rid of a square root, I need to square, and that'll happen to both sides. So be careful on doing this left side. Make sure that you take the squared and square both the numerator and denominator. So we're going to get x squared over 4 because 2 raised to the second power, or squared, is 4. And then we'll be left with, this cancels with that, and we're left with y minus 3. All right, so continue solving. We just need to add 3 to both sides. So plus 3 on both sides, and that leaves us with x squared over 4 plus 3. These cancel, leaving us just y. All right, so let's plot that and use the plot to decide what we might need to do about our domain or range. So looking at Desmos again, when I plot this, I see that, I get a parabola because I have an x squared. So I'm going to need to restrict things in order to not have a parabola. So I'm going to go in, and if you go to your ABC keyboard, you can find the bracket there. And I'm going to go in and say that I can't have any x values that are less than 0, because when I do, so I need x greater than 0. So now I have that perfect mirror image reflection, not a double image and only half of it is a perfect mirror image reflection. All right, so we are going to have to actually include that as part of our answer. We're not going to be able to take care of it by getting rid of a negative sign or something like that like we did before, because there's not any negative sign to get rid of. So let's go ahead and take a look. So step number 4, and again, that's kind of based on peeking at our graph, is that we needed our domain to be greater than or equal to 0. So again, we had to restrict it because it was going to give us that double image that we didn't want. Plotting here now, we've got, let's see, we had 7, 4, so we'll have 4, 7. Nope, that's a little too high. 7 is there. All right, so I will draw my graph. Looks something like that. All right, and there's our inverse. Okay, so we can again write this in our inverse notation, function notation. We can say f inverse of x is equal to x squared over 4 plus 3. And again, part of our answer has to be that x is greater than or equal to 0. Okay, so don't forget that part. That is a critical part, otherwise it's not actually the inverse. All right, so we've taken one function and determined the inverse. Now I'm going to give you two functions and determine if they are inverses. So that is our next topic. We want to know, are the following equations inverses? So this is our method for doing that. We basically pick one of our functions. It doesn't matter if we pick f or g, and we determine the inverse, just like we've been doing. So determine the inverse of one function. All right, and once we determine the inverse of one function, we want to see if it matches, if it's just the same function as the other one. So if it matches the other function, then we know that the two functions are inverses. So let's take a look at this first one. We have f of x is equal to 3x minus 1, and g of x is equal to x plus 1 over 3. We've got some of the same numbers here, so maybe it's a potential to get something going here, but let's take a look. So I'm going to pick g. It doesn't really matter, f or g. I just picked g because I was like, oh, it's already down here at the bottom. I won't have to rewrite it. So step 1 here, and then step 2 is to write it changing x and y. And now step 3, I'm going to use green. Step number 3 is to solve. So in order to solve, I need to get rid of this 3 that's being divided. So I'm going to multiply both sides by 3 in order to get rid of the 3. So we're going to be left with 3x is equal to y plus 1, and then just simply subtract 1. And 3x minus 1 is equal to y. All right, no squares or cubes or anything here. And this is our inverse of function g. Our next question, does it match function f? So look at that function and this one. Are they the same? Yes, they are the same. So the functions match when I took the inverse of one of them. So our answer is yes, they are inverses of each other. Let's do this one more time. And you might want to pause the video here and try this one on your own, and then come back to me and let's check your work. So start off now, go ahead and pause the video and try this one. Okay, so let's go ahead and go through our steps. Step number 1, I was using pink for that, is just cross it out and make it a y. Step 2 is to switch x and y. So we're going to have cubed root of 2y. How do we get rid of a cubed root? By cubing. So this one and that one cancel, and we have to cube the 3. So x to the third is equal to 2y. Divide both sides by 2 to give me x to the third over 3, or x cubed, sorry, over 2 is equal to y. Okay, again, compare these two. Are they the same this time? No, not the same. So our answer is no, these two functions are not inverses. All right, we have one last little topic here, and this is dealing with multi-step real-world problems. Those of you that have been in geometry have seen some of these. Some of you that are in physics or IPC have seen some of these. Probably not called an inverse function. It's basically just taking a function and solving it for a different variable, but it's the same process as switching our variables. However, when we're doing real-world problems, there's a very important thing to note. You do not, notice that's capitalized and underlined. That means it's important. Do not switch the variables. Okay, we are just going to take an equation and solve it for a different one of the variables. So let's take a look at an example. We want to find the inverse function that represents the surface area of a sphere. So surface area of a sphere, S, is equal to 4 pi r squared. So think about that for a second. If you switched around the r and the s, then suddenly r would stand for surface area and s would stand for radius, and that doesn't make sense. Don't switch the variables. But what we are going to be doing is solving for r. So we want to solve for r. Why do we want to solve for r? Because we want to find out what r is when we have an s value, a surface area of 100 pi feet squared. So let's go ahead and take a look at that. We're going to start with our original function, and we're just going to do our steps to solve for r. So I want to get rid of that 4 and that pi to start. And that'll give me s over 4 pi is equal to r squared. Now I need to take the square root. Let's use orange. Take the square root of both sides so that these cancel, and I'm left with square root of s over 4 pi is equal to r. Now let's think about that for a second. Normally at this point we would put in a plus and a minus in front of that square root sign, because when we take the square root of both sides we have to account for positive or negative values. But does it make sense to have a negative radius? Remember, radius is measuring a length. It's the distance from the center of a circle to the outside of the circle. So it makes no sense to have negatives. So let's make ourselves a note of that. Let's don't use the plus and minus, because a negative radius doesn't make sense. So sometimes whenever you are doing real world problems, you have to put a real world thought into it. All right? There's no such thing as a negative distance. Okay, so now that we've solved for r, we can find out what r is equal to when s is equal to 100 pi. So we're just going to plug that in. R is equal to square root of 100 pi over 4 pi. Let's simplify this. Our pi's are going to cancel out, and 100 over 4 can be reduced to 25. And then if I take the square root of that, I'm going to get 5 feet. Square root of 25 is 5. So our radius is 5 feet when our surface area is 100 pi feet squared. All right, let's take a look at what might be a physics problem. So the distance in meters that a dropped object falls t seconds on Earth is d is equal to 4.9 t squared. Notice that we have a decimal starting out, so we're probably going to have a decimal answer. Solve the equation for t, so we're finding the inverse again, and then determine how long it takes for the object to fall 50 meters. So we're just going to start out like we've been doing. Again, don't change the variables. It makes no sense to call d equal to time, or vice versa, t equal to distance. So I want to divide by 4.9 on both sides. So d over 4.9 equals t squared, and then take the square root. Let me change colors here so you can see that's a different step. And so the square root and the squared will cancel, leaving me with square root of d over 4.9 is equal to my time. Again, don't use the plus and minus. Just like distance can't be negative, neither can time. Haven't found a time machine yet, so we can't go backwards and do negative time. T can't be negative. All right, so let's plug in for our particular case. So we are going to take our 50 meters here and substitute that in for d. So if we have our equation, t is equal to the square root of d over 4.9. We want to substitute to say t is equal to 50 over 4.9. And because we started out with a decimal answer is going to be perfectly acceptable. Just stick that in your calculator and you're going to get 3.2 seconds.